So in this talk, I'm going to talk about some ongoing work with Nima and my student, Huan, who is at Caltech. It's been going on for a while, so some of you might have heard a various version of it. Of course, we have some new updates, and I'm optimistic that we'll have it out this summer. And also, there will be some discussion about where some of these results are already been applied to specific cases. So this will be this is about a paper that we put out earlier this year. So in recent years, study of perturbative scattering amplitude. So there's been an emergent geometry that has been found, and this emergent geometry is what we now term as positive geometry. And what positive geometry means just means that the geometry itself is defined by various positivity conditions in the space in which your scattering amplitude lives. And so various examples now are sufficiently understood to a particular extent. So for example, n equals 4 super Yang mills for all loop planar order is known as given by, the integral is given by the amplitude hedron. And even for the plain vanilla adjoint phi cube theory, there's also a polytope understanding of what the scattering amplitude of that theory is. So the presence of this geometry can be, well, you can trace back basically to, it's just a principle of locality and unitarity of the theory, and that these two combined gives you this polytope structure. But you can also turn this thing around and say that, oh, well, actually this polytope, this geometry structure is a unification of these two, because usually when we talk about quantum field theory, we talk about locality, and then later on we impose unitarity to the theory that we have. But and you can turn this around and view that this is a way to formulate these two principles as a unified principle by employing this geometry. Of course, there's only you can say that there's only a handful of examples that are known so far. So you can ask that if this is really a reflection of some new fundamental principle of general QFTs, we should be seeing more of this. And if we're supposed to see more of this, where would we want to see it? And another thing is that in these constructions, Lorentz invariance is just given in the sense that the space in which your scattering amplitudes are defined, Lorentz invariance is already embedded. For example, for the phi cube theory, you're talking about the space of Mandelstam variable. So Mandelstam variable, when you give it, it's already Lorentz invariant. So you might want to ask, can you really just give something in which the Lorentz invariance, or at least the Lorentz invariance in the UV theory, that the requirement that in the UV is Lorentz invariant, is actually not manifest, and it's actually emergent. So these are and now let me turn to another point of view, which thanks to Sergey and Ricardo, that they've told us long ago, that there are from the effective field theory point of view, there's actually interesting positivity bounds also from the S matrix. And it was known long ago that the leading four derivative coupling in the theory, in the general EFT, should be bounded. They should be definite positive. So let me just go through this argument very quickly, because we're going to extend this very soon. So the statement is that the coefficient, you can pick out the coefficient from the scattering amplitude, the 4-point scattering amplitude, and the Fourier limit by doing this contour integral, where the contour encircles the origin, and therefore you pick out this coefficient. But then you can do a contour deformation, and by using either the Forsyth bound or sufficient assumptions about how this amplitude behaves at infinity, you can drop the infinity contribution, and basically what you just pick out is just the imaginary part on the real axis, which from the optical theorem or unitarity tells you it's the cross section, and therefore this is a definite positive integral, and then you have a definite constraint on this coefficient. So basically this basically utilizes the optical theorem. And actually, if you assume that your UV completion is perturbative in the sense that you can suppress the massless branch cut, then you can actually have a large number of positivity bound for each order and derivative expansion in the Fourier limit. So in this context, we can also ask the following questions. Can we probe the details of unitarity and Lorentz invariance in the UV? So what I mean is that in some sense, this is really a coarse-grained constraint, because all you're using is just the optical theory. You're using that this is just given by the cross-section. But you also know that you also know much more, because the optical theory tells you that there's an expansion in terms of the partial wave expansion. The partial wave expansion is expanding this thing on a particular set of basis of functions. So is there any way in which that this basis of function, this information is actually appearing in your IR theory? And also we would like to ask is, can you differentiate? So for example, when you're doing this, you're basically for example, you're constraining the fourth derivative term, and any operator out of fourth derivative term are just all coming into this constraint. So in a sense, you're not differentiating between the different possible operators of four derivative terms, because you know that if you have, and as you go with more and more derivatives, you know that there's actually more and more different kinds of operator existing. And so this is another way of saying that this is not a fine, this is a coarse-grained constraint, because all these operators are just collapsing into just a single constraint that it has to sum the positive. Can actually start differentiating these operators. So these two questions actually is nicely combined to a single picture. So in this talk, I'm going to talk about general coefficients for your effective theory. Now, so I'm going to map the coefficients of your effective field, the higher dimension operators, into the scattering amplitude, of course. And so we know that if you have effective theory description, that means that in infrared, your scattering amplitude is given by the presence of massless poles and a polynomial expansion in terms of your Mandelstam variable, where the Taylor series expansion to coefficients are going to be linearly related to these coefficients. So first I want to address the question is, when are these coefficients well defined? So when are these Taylor series coefficients well defined? So of course, if the UV theory, if the UV completion is well, I mean, let me just say why there's an issue about well-definedness. It's because when you're computing the scattering amplitude and you're saying that there's a perturbative expansion, that means you have a Taylor series expansion. You want to be able to do residues to pick out these coefficients. But since this is a massless theory, so you might worry about massless cuts. So you need to deal with how the massless cuts, or how to avoid the massless cuts. And so it depends on what your UV completion is. Of course, if your UV completion is perturbative, for example, a linear sigma model or string theory, in the sense that there's a perturbative parameter in the UV that is still present in the IR, then you can just use this perturbative parameter to separate between the massless branch cuts and the massless branch cuts from the tree part. And therefore, you can define these operators cleanly by doing the usual Cantor integral. So now we're not just doing the Cantor integral in S, we're also going to do an expansion in T. If you don't have this perturbative parameter in the UV, then you just have a direct massless branch cut coming all the way down to the origin. Then in this case, you basically, what you can do is just deform your Cantor integral. So you deform, you're defining, in a sense, a generalized version of your effective theory coefficients. And this coefficient is defined by moving the poles away from the origin and into the complex plane. And just to give you an example, so if you do this kind of deformations, then the generalized coupling constant is going to be a linear combination of the would-be the original effective field theory coupling constant. So it still gives non-trivial information. And and so generally you have these two cases. So it depends on what you assume for your UV theory. And from the remaining of the talk, all of the constraints just apply in both cases. So yes, you will have a question. Yeah, but it goes through a non-perturbative regime, right? I mean, the pion, it goes through the confining regime.
But let's say we complete that to the linear sigma model. Still, we go at low distances, that there will be IR logs.
Yeah, so so you can do it in either way. So I can do the IR logs with this. So this way you can deal with the IR logs. So yeah, so of course, so this is because I'm picking 5, 6, and 7 derivatives. For that case, if I do the lower derivative part, you'll see that there's going to be a linear combination with the log contributions here. So the log will be there, and the IR logs you can say that it's essentially regulated by this mu square, this deformation. And you still have positivity because this is a definite positive integral. Okay. Now another thing is that since I'm going to do things fine-grained, so I'm moving away from the 4 limit. So as you see, I'm doing an expansion away from the 4 limit. So my t is not going to be 0. There's a good thing that my t is not going to be 0 because I can do various continuation when you have massless cuts. The cut actually opens a little, so you can do continuation across this region here. But then you have to worry about the famous threshold singularity. So it's not true that the discontinuity of your scattering amplitude is all just given by multi-particle production. So if you have non-trivial t, what you have is you have singularity. So for example, even the two-point functions, if you have some off-shell two-point function, it's not true that the discontinuity is always just given by the multi-particle cuts. In principle, you can have the singularity is associated with these propagators going on shell. Of course, in the two-point function, this doesn't give you a problem, but we're considering the four-point amplitude. So even just the simplest four-point massive box amplitude, you can already see this problem. So this is the massive box. This is the integrated result. And you see that this continuity is given by these functions, beta nu, beta nu, and beta nu nu. And these u and v are just 4m squared over s and 4m squared over t. So here, these are the usual, what you will call the usual particle production threshold singularity, which starts at 4m squared. But then here, there's an extra piece here. And this extra piece precisely corresponds to this threshold singularity. And that piece corresponds to the possibility of putting all four propagators on shell. So that if you move away from the lower limit, the discontinuity is not multi-particle production alone. There's going to be various different new kinds of singularity. And so you need to be careful at this. But because of the fact that we're only going away from the forward limit at small t, as you can see, that if you go to small t, if the t is much smaller than the threshold, the uv states that you're integrating away, these things go to infinity, so this threshold singularity goes away. So the boundless threshold singularity can be avoided if t is much smaller than the threshold or whatever uv scale. And since we're around the forward limit, t is very small. So we're safe from these two issues. So the setup is the following. So we're going to consider our general scattering amplitude with t much smaller than whatever the threshold singularity is. Then we have a control over what the analytic structure is. Now we can do positivity bands. And what I mean is that the analytic control is that we know that in the origin, we basically just have either the massless pose and the polynomial expansion. Going away from the origin, there's no new singularity on the complex plane because of the absence of threshold singularities. And then you just only have poles and branch cuts. So what is important in this whole talk is that we know that the poles and the branch cut, the residue of this pole and the discontinuity of this branch cut is expandable on the Gagenbauer polynomial basis, which is the generalization of Legendre polynomial beyond 4 dimensions. Because I'm assuming what my UV physics is, it might be higher dimension, it might be lower, it might be 4 dimensions. So I'm going to use general Gagenbauer polynomials, and more importantly, it's a positively expanded. So at tree level, the positivity is straightforward. It's just the fact that this coefficient is the product of the 3-point coupling. At loop level, it's slightly non-trivial that you have to go through a little bit proof. And basically, yes?
Isn't your analysis general? So what are you talking about loops? You said that you did not have any weak coupling. You're talking about loops in the Lagrange effective field?
No, I'm talking about loops in the UV states. So the UV states might come in loops. Yeah, so I want to do things general, so I want to include both cases. Yeah, so I want to do things general. Yeah, so if I have UV loops, and so if actually the case that in the later case where I'm going to apply these bounds, it's going to be massive loops.
Is M is the mass of you got the light particle, or
M
M is the UV?
is the UV degrees of freedom.
M is the UV.
Yeah. So these are coming from the UV degree, the UV loops. So yeah. I mean, depends on the process. The UV state might loops. And so here, you can go through and you can prove that basically it's also expandable with something like a spectral parameter, except that this spectral function is not a 2-point spectral function, it's a 4-point. So it actually has a spin dependence on it. So and then of course it depends on your center of mass energy. But this, as the usual 2-point spectral function, this is definitely positive as well. So this will be the central information that I have, is that I have control over this discontinuity, and I know the way that I know that it's a positive function that is expandable on this basis. So right. So then now we can do by assuming certain behavior around this counter and infinity. So for example, so we know that the amplitude should be bounded by s squared. At most, it can be s squared. So that means that the counter integration is going to vanish for n bigger than 2. And therefore, this means that you can pick out the coefficients at the origin. The Taylor coefficient is going to relate it by this complicated function here, which this is given by the tree part, and this is given by the discontinuity part. And principle, you might say that this is a useless constraint because of the fact that these are completely all unknown. You don't know what the spectrum of the UV state is. You know where you don't really know where the branch cut starts. So you're saying that on the right-hand side, I have infinite degrees of unknown. I mean, what does this? I mean, this equation shouldn't tell me anything. But of course, we know that it tells us a lot. So just the previous forward bound, the forward limit bound, you can also see directly from this equation already, because the space age of forward limit just corresponds to t equals 0, and that's just translated to all of these Geigenbauer polynomials are evaluated at 1. And which you know that if you look at all the Geigenbauer polynomials and you look at the argument, you see that it's all definite positive beyond 1. So you know that this is definite positive function.
Okay, so
Yes.
you have a UV theory where there is no form, right? There are no stable particles.
Okay.
So you can have a situation
So-
like when you have some strongly coupled thing where you don't have any form. You start with a branch cut.
Yeah, sure. Then I don't have this piece. I just start with here. Yeah. So like as I said, I'm just doing general analysis. So I'm not assuming anything. So good. So now instead of just sitting, so this is the previous. So in a sense, you can see that the previous forward limit bound is really just the tip of the iceberg, because in principle, now we're going to actually really probe this Geigenbauer polynomial. So we're going to do this Taylor series expansion in T. Okay. So if you do the Taylor expansion in T, so what you're going to get, so I'm going to define my vector VL as the Taylor coefficients for expanding this Geigenbauer in T. And so therefore, if you expand this, you're basically saying that the coefficients of these Taylor coefficients are given by a positive sum multiplying by these functions. So let me just organize this a little bit. So I can organize, for example, by the way, K and Q. So I'm organizing things in this way. The first label K, the second label Q. The first label is giving you the total mass dimension or the total derivative counting. And Q is basically how many powers of T you have. So in the forward limit, Q is 0. And the more higher in Q, you're basically going away from the forward limit more. So for example, for fixed mass dimension, for fixed K, I can go higher and higher in order in Q. So basically the same is that these coefficients must given by a positive sum of these vectors here, where these vectors are basically defined by the Geigenbauer, the expanded Geigenbauer polynomial expansion. No, but
So this expression that you have done, these G's, all these, does or doesn't involve the addressing the loops of the light states?
the loops of the light state. Oh, yeah, so this was a bit before. So that comes back to how I define my coefficients here. So before, as I say, that if the loops of the light state can be suppressed by some perturbative coupling, then I can just suppress it and choose not to discuss it. That would be. If they're not suppressed, then I need to go to this more more refined definition of what I mean by the coupling constant. So I need to do my counter. So everything follows through. It's just that the S integrals that I was doing previously now is moved off to the complex plane. So now these coefficients must also satisfy the bound that I'm going to give. So it's these coefficients that are satisfying the bound. And these coefficients are related to the original coefficients through some linear combinations. Yeah.
But that M, in the case where you have
That's the
this
loop, that
scattering,
contains a lot.
that contains everything.
Yeah.
But it can be written the same way as you wrote before?
Oh, you mean yes, actually, yeah, even the massless cuts. So that's also fun. If you do the massless cuts, you can also see that the massless cuts, you expand it on it, and you also have the positive
That structure.
component. Yeah, it's actually the same thing. There's a caveat in that. It requires that the theory doesn't have collinear singularity. So in other words, the massless, so the effective theory that you start with doesn't have massless 3-point. If you have massless 3-point, then of course the cut is going to have singularities in the cut, and then you have to do it and deal with it with some other ways. But for example, if you have a pion theory, QED doesn't have massless 3-point. QCD, for example. Yeah. If you need massless quark, or I'm sorry, massless electron. Yeah.
But even in the limit,
Yeah, QED.
But QED in the limit of a finite mass. Okay, you're saying you go.
Yeah. So, yeah. So yeah. Okay. Oh, I'm going the wrong direction. Sorry. Yeah, so basically this statement is that these coefficients, when you combine, they're given by a positive sum of these vectors here. So this notion gives you a notion of, so this is what we call the convex hull. So that means that the coefficients are bounded by regions that are defined by the convex hull. And just for those who are not familiar with what convex hull is, it's actually, you actually are familiar, because you're familiar with the notion of center of mass. So when we talk about center of mass, we talk about, for example, a bunch of points weighted by positive coefficients, and that gives us the center of mass. So the center of mass is going to be inside this bounded region. And so if the mass can be anything, then that just means you're scanning through all the possible places inside this bounded region. So in other words, for example, in the two-dimension case, then the possible places where the center of mass can live to this positive region. So the polygons, you can define a two-dimension polygon by defining it through this kind of convex Hull approach. And of course, you can extend this to any dimension, and then you will have a polytope in arbitrary dimension. So basically, you were saying that the region the region where something can appear is given by the positive sum of these vectors. Then this region is given by the convex Hull of these vectors, and that region corresponds to a polytope region. So basically, the statement that I have here is that the coupling constant is lying inside the polytope. And so now we're going to be interested in what the shape of this polytope is. So, so we can go through this in two different directions. So first of all, so we have this relation here, so we can consider fixed mass dimension. So now I'm organizing my coupling constant in this form, these higher dimension operator in this form. So in each row, these are the same expansion in T order, and each column is the same mass dimension. So for example, I'm interested in 4 derivative terms. So I have 3 possible operators, G20, G21, G22, corresponds to how far I'm going away from the theta equals 0. Then the statement is that these G's, this 3-dimension vector must sit inside the convex Hull of some vector here, where all of these vectors are given by the Taylor expansion of your Legendre polynomial. You can do it the other direction, which is consider fixed Q, which is I'm considering the fixed degree and angle. I'm now considering different higher dimension operators. So this is 2 derivatives, 4 derivatives, 6 derivatives. I can combine them. And now that it's telling you that it must sit inside the convex Hull of a vector that looks like a moment. So it's x squared, and x cubed. So as you see, it's very constraining if you use this information. It's telling you a lot about where these higher dimension operators can live. So first, now these 2 cases where I have fixed mass dimension and fixed angular dependence, the reason I do, of course I can do this analysis in various different ways, but I pick out these 2 cases because of the fact that they really reflect a different part of your theory. So basically we're assuming that your UV completion is basically can be given by all the resonance. So now I'm putting everything as a sum. It's just because I'm not differentiating between cuts or single particles. It's just going to be a continuous sum. And I'm not assuming whether my spectrum is continuous or not. So from now I'm just going to use a summation as an indication. So I can do, so basically I'm saying that you can do a Taylor expansion of this. So the Taylor expansion of your numerator, that gives you the V vector, so that's a reflection of unitarity plus Lorentz invariance. Lorentz invariance is now encoded because I'm expanding in this polynomial. It's Lorentz invariant that tells me I should expand in this polynomial. And also I have the expansion in S, so the expansion in S is a reflection that all the singularity is occurring in the real S axis. So it's a reflection of locality plus unitarity. So these 2 geometries are reflecting separate properties of your UV theory. Good. So now we want to determine what is the boundary of this convex Hull. And can we determine it? And naively you would say, no, there's nothing to do here. The reason is because of something that I glossed over, which is actually when we write this sum, you can ask what are the number of L's that we have. Of course, we don't know what UV completion is, so you might say that at tree level we don't know how many sums you should sum over, but you have an idea that there's no fundamental spin 2, so this should be bounded by 2. But once you have that you're actually also considering the possibility that the UV states are coming through loops, then this sum goes to infinity. It's just because that, and when you have discontinuities in the loop, you basically have two particle production, and they have relative orbital, and they can be any spin. So this sum goes to infinity. So what is the problem? Well, the problem is that you're asking about what is the convex hull of infinite number of vectors. So that's the problem. You don't know how to do it. The complexity is infinite, because if you by what I mean by determining the convex hull is, I mean determining what the boundary is. Basically, it's well known that if you have n vectors in d dimension, the complexity of this computation is n to the d over 2 factorial. And since n is going to infinity, there's nothing to do here. I mean, it's just too complicated. But nature is very kind to us, because nature gave us a very special set of vectors. So if you take these vectors, so for example, this is very fun. You can just take your Mathematica and do this expansion. You take each spin, each Gegenbauer or each Legendre polynomial for each spin. You do the Taylor series expansion. So I did it for you. So this is for the Legendre polynomial. This is spin 0, spin 1, spin 2, spin 3, spin 4. First of all, you notice that everything, each order in expansion is actually all positive. But the more remarkable thing is that the determinant is also positive. In fact, you take any minor in here, it's always positive. So the determinant of the ordered vectors, they're always positive. Okay? So this is for the vectors that you get from expanding the Gegenbauers. So you can also expand the propagators here, which, as I mentioned, it gives you the moments. And you can also do exactly the same things for the moments. I mentioned that the moments just x1 square, x3 square. This is simple. You know that the determinant of this is just the van der Waals determinant. And you know that as long as these x are ordered, then this is also definite positive. Okay, so the set of vectors that we're talking about have a very special property that any times it's ordered, the determinant is just going to be positive, the minor is going to be positive. Why is this important? Because then that tells us that the boundary is already known. There's no computation to be done. Because the convex, so whenever you have a set of vectors with some particular ordering, and the ordering are all, and for a given ordering, it's always positive, then the convex hull is what is called the cyclic polito. It's just known already in mathematics. And for a cyclic, it doesn't matter how many number of vectors you have. You already know exactly what the boundaries is. So depending on your dimension, if dimension is 2, then the boundary is just I plus 1, where I and I plus 1 is the order that you had before. For 3 dimensions, it's going to be 0, I plus 1, I plus 1, infinity, and so on and so forth. It's very easy to see why these are the boundaries. So in light of time, I'm just going to skip the discussion of why, but to just let you see what the constraints are. So since, for example, let me go to k equals 2, which is the 4th derivative term. So for the 4th derivative term, as I mentioned, there's 3 operators. So now I'm saying that these 3 operators must lie in the convex hull, which the convex hull is given by VL plus 1 for all the possible spin vectors. So let's see what this constraint is. So we're going to consider the operators that are associated with s squared, st, and t squared. Of course, from symmetry, you know that the coefficient for s squared has to be the same as coefficient for t squared. So basically, you really have just 1 degrees of freedom, which is a ratio between the ts over the s squared. So you can put this into the bounds. So x, this vector here with 1, 2 has to be bigger than 0, 2, 3 has to be bigger than 0, and so on and so forth. And then you can see that actually the tightest bound is given by the first one. So you see the constraint now is that bigger than 0, G21 has to be bigger than 0. But also, the ratio between these two has to be smaller than 8 over 3. Okay, so the relative ratios of these two operators are actually bounded. In some sense, you can say that this is expected, or I can put it another way, is that there's no way of fine-tuning in your UV, such that in the IR for a fixed mass dimension, certain operator is there and certain operator is just completely not there, because the ratio are just bounded in this case. And so this is a reflection of this intuition that there's no fine-tuning that you can play around in the UV that does this. You can, of course, then I can go beyond. I can go to 6th derivative order, and you apply exactly the same procedure, and then you found that there's also a bound for the s to the 3rd and the s squared t term. So that means I have 10 minutes, or? Oh. How many minutes?
7.
7 minutes? Okay, great, thank you. So let me just go a little bit more. So for example, if I go to 10 to the 10 derivative terms, now after adding the possible symmetry to your theory, you basically have two degrees of freedom, which are the ratio between these operators. So just give you a feeling of how constraining this is. So I have two sets of bounds that take this form. And this is the bounds that you have for one set. So the colored region are the allowed region, and the non-colored region are the ones that are ruled out. And so you see that these two sets of boundary are basically carving out different regions. So this is saying that this part is completely ruled out, and the other part is saying that the lower part is completely ruled out. And so so the combination of these two is basically this very small region. And again, this gives you the x and the y axes are basically the ratio of these different operators. And the same is that it's the same thing, that these ratios are actually tightly bounded by this analysis. And you might say that I'm really just talking about the scalars on the outside because I've been expanding my 4-point amplitudes on the Geigenbauer polynomial. But you can also do this for if you want to have photons on the outside, or graviton. Of course, for graviton there's going to be collinear singularity, and that has to be taken care of. But assume that if we just directly apply it, then there's really nothing you need to change. All you need to do is just change the Geigenbauer polynomial to the Wigner D function, which was also mentioned yesterday. And these are the bases that you can do to expand when you have spinning particles on the outside. And so what is again remarkable is that if you take the Wigner D function, you do exactly the same thing I told you to do. So this is for when you have photons on the outside, and this is for you have gravitons on the outside. So this is expansion around theta equals 0. Then you see that again the matrix are all positive, and you can directly check that again the determinant is also definite positive. And so that means that again, even for spinning particles, nature gave you a cyclic polito, and the same constraint you can apply again. So for example, we can do so. Let's talk about gravitons. So if we have 4 graviton interactions, so this would be constraining. So let's just look at so this would be R4 in front. So this will be D to the 4 R to the 4 operator. So there's 2 different configurations, and basically telling you that the ratio between this has to be bounded by this coefficient. And you can also go beyond the 4 derivatives, multiplying by R4, and then you have this region where it's bounded. So there's really an infinite series of that bounds these higher dimension operators, just coming from this assumption that the UV is given by these, or the amplitude in the UV and T near 0 has this nice Geigenbauer expansion. Good. So this was talking about the bounds coming from expanding around the 4 limit. You can also talk about bounds where now I'm sitting. So let's just, for simplicity, I'm going to sit exactly at the 4 limit. But now I'm going to talk about all the different derivative orders in my operator. So I'm going to talk about S squared, S4, and I'm going to combine everything. The same thing tells me that these coefficients, so this is S to the 4, S to the 6, S squared, S the 3rd power, S to the 4th. And this is basically the same analysis telling you that it's given by the convex hull of this moment vector. So it takes this form, but more importantly, the moment vector has a very special further bound, which we prove, and it's that if you organize these things in what is called a Hankel matrix, so you organize things symmetrically, G0, G1, G2, G1, G2, G3, and you organize them, the determinant of this is definite positive. So now I have a bound, and this bound is interesting because this bound is a nonlinear bound, because when you take the determinant, this gives you a nonlinear, this gives you a polynomial. So let me just go very fast, just show you an example of how I'm going to use this. So let's consider a EFT in 3 dimensions, and this EFT in 3 dimensions and since there's no graviton in 3 dimensions, I only have photons. So this is the EFT of photons. I'm getting this EFT by integrating away a single massive state, okay? And so I'm integrating the single massive state, and so all of these coefficients are now going to have contributions that are, so I'm going to parameterize, I'm going to use this parameter Z, which is basically the charge to mass ratio weighted by n Planck. So these coefficients are going to have Z to the 0, Z squared, Z to the 4. Coming from the Z to the 4 is just the massive particle in the loop. this is the massive particle with some graviton exchange. Of course, there's no massive, there's no physical degrees in your graviton, but there's still a non-trivial amplitude in 3 dimensions, and this will be just the neutral part. So I'm going to do the bounds on this coefficient. I'm going to apply the bounds on this EFT, and let me just go very fast. The important point is that this EFT I can compute. These coefficients I can compute analytically because I know what the amplitude is. So we've computed the coefficients. So the amplitude is given by scalar triangle and scalar bubble, and these are the coefficients for amplitude. And once you have the coefficients for amplitude, you can just directly get the 4 limit coefficients. So let me just go real fast. So
zero power you can compute?
yeah, we can compute that. Yeah, and because it's just using unitarity method. Because okay, maybe I'll in the question section. So these are the coefficients that the analytic coefficients you have for any order in derivatives, because we know the amplitude, so we can compute this to any order in derivatives. So we have these coefficients. So all we need to do is just stick it into this bound, and then we compute. And when you compute, you find an interesting, for example, if you apply this matrix, the determinant of the matrix needs to be positive, and we've computed, so k to the 200, so this is basically 80 times 80 matrix, so you can just order by order just increase your matrix bound. And this gives you a bound on your z. So the z is actually bounded between 0 and 1.02, and z must be bigger than 34.82. So let me just spend 1 minute explaining what this actually means. So this is basically saying that there's 2 regions of z that is bounded between 0 and a. Sorry, this should be equal. This is not just smaller, but smaller and equal. And then z must be bigger than b. So of course now I can further increase the size of a matrix. The fate of a and b is very different. So as you see, so let's just focus on the blue line here, which is here. The fate of a, which is this region, is asymptotically going to a fixed value. So it's somewhere around above 1. However, for b, this bound is just linearly increasing. Okay, so if I can trust my extrapolation, then this is saying that basically large z is forbidden, and the allowed z is actually only around here, between 0 and 1. So this is the opposite of what you would expect for weak gravity conjecture, because in weak gravity conjecture you would think that this requires you have some z always have to be bigger than 1. This is actually telling you the z bigger than 1 is actually is not favored. Of course, this is the reason that you see this is really because of the EFT that we started out with. So this is really the EFT and low energy is dominated by the lightest particle, because it has this mass here. So if I have a separation, so basically what this is saying is that, so this analysis is saying is that if you have a single light electric particle that is isolated from everything else, then this is in contradiction with this bound. If I have a single light electric charge particle, and so if you think about the standard model, then so we're not going. So there's a lot of things to discuss whether I can compactify it to 3D. But let's say if I have a standard model like spectrum in 3D, where I have a light electron and there's no light states around there, then this would seem to contradict this bound, and this doesn't make any sense. I mean, in principle, we expect that we can compactify standard model in 3 dimensions. And of course, the reason is that the standard model is that I only included this charged particle. It might be that there's actually other light particles around. And indeed, if you see that you add other light particles, so this is just showing you the other light particle. So this was the original, which is a single charge particle. This bound is going to infinity, which is removing, so which is bounding, which is saying that anything with z bigger than 1 is just not favored. But if I include a light particle, which I call this beta, sorry, I'm really going fast, so let me call this. Yes, so for the light particle, I'm introducing a new particle with beta, which the beta measures the ratio between the electric charge and the neutral charge. Then you see as beta goes bigger, this is actually, this ruling out slope is actually tending to 0. So actually the presence of light particle alleviates this bound, and depending on how light you want to, and it's actually important that the light particle is lighter than an electron. It cannot be bigger, because if beta was bigger, so for example 1/4, this bound doesn't change at all. But once it starts going beyond 1, the bound just actually comes down. So, okay, so I should finish here. So basically this is interesting. So you can see that this is interesting, that this actually provides you non-trivial bounds on realistic such scenarios. So yeah, so let me just finish. So I hope that I convinced you that this union of Lorentz invariance, locality, and unitarity, it really gives you a large number of bounds for the space of couplings and dimension 8 and beyond. And the operators are basically live in the space defined by the intersection of different positive geometries, as I showed you. There's a positive geometry associated with the Gegenbauer expansion polynomials and also from the moment curves. And really, we were only scratching the surface of this geometry because I haven't told you what happened when I actually cheated you a little bit in that I actually just showed you the bounds that I get from if I only have S-channel exchanges. If I have, so in realistic such scenario where we actually use, you actually have huge channel contributions. And these two actually talk to each other in a very interesting way. And we're still in the process of understanding the combination of these. Of course, we can just write down the bounds, but what is the mathematical structure that corrects the bounds, that constrains the bound? And I'd just like to mention that exactly the same kind of structure is appearing in a wide set of different physics problems. For example, in one-dimensional CFD bootstrap, for modular bootstraps, of course, as we know, amplitudes and gauge theories and gravity, and even recently connected to the sphere packing problem. So this is a very interesting thing that is appearing in various different aspects of physics. So thank you very much.
And you promising to finish by the summer?
Yes, now that you ask, it's recorded, and yes, now I have a legal.
So when I go back to the question I was asking,
Yeah.
you said it's the z to the 0 is calculable, but you just showed if you add another part, you shift it. So it's UV sensitive, no?
No, it's calculable in the sense that
Which I thought it was what Schungerheimer were claiming, that you cannot calculate that part.
no, what they mean that you cannot calculate that part is that this part, all right, so just also an important point why I was doing this in 3 dimensions. So if you compute these, that these are UV divergence in 4 dimensions. Since they're UV divergence in 4 dimensions, that means you need to renormalize it. You need to renormalize it, and so that part is not calculable in that sense. You don't know what the renormalization condition is in 4 dimensions. But in 3 dimensions, these one loop processes are just UV finite. So that ambiguity is not there, and that's why we actually started in 3 dimensions.
When you introduce these light neutral particles
Yes.
to try and bring the slope of your line down, it looked on the graph like you still always have a positive gradient.
Yes, but however,
so if I go to arbitrarily high n,
well, but you have to see that you have to. Let me just show you the slope. Yes, but I'm going to. Why do I keep left and right? Yes. But you see that we were only plotting to beta is 13/4. This is they're still very close to each other, but they're actually already going to 0 very fast. So again, so what beta means? Sorry. Why am I so always confused? Yes. So what beta means is the mass of the electric particle with the neutral over the neutral particle. So I'm only going to 13/4. So I'm not even like the factor of 10. I'm not even there yet, and it's already coming down to near 0. So right. So that's what But the issue here, the reason that we haven't gone, it's just computation power. We just need to improve our computation to really start to probe these large beta regime to see how if it actually goes dead. If there's actually the question will be, is there a critical beta which gives the slope is just 0? And that's the question we want to answer.
right, I see. Okay, so it sounds like there's some kind of order of limits here, right? Where you want beta to be bigger than whatever the maximum n is, right?
You're saying that you see that the beginning is actually pushing higher and higher away. Is
Right,
that what they're saying?
right,
Yes,
exactly, yeah.
indeed. That's so so as you see, so the constraints, as you push the beta higher, the first place where the constraint appears is actually higher and higher in matrix, right? So that's why I said there's an issue about computation power, because the matrix size is growing.
Yeah.
When I start, yeah.
Okay, I see. Okay, thank you.
Yes.
So if I understand correctly, in this last part you're discussing gravity in 3D, right? So
Yeah,
are you
that's it.
sure there is this matrix there? Because things are conical deficit, there is this singularity related to that, and it's arbitrary and on 0t.
Yeah.
Which-
So actually, of course, well, let me put it this way. So at least from an S matrix point, at least that's at least yes, we don't see. Yes, we don't see any thickness at the perturbative level. So
No, but sorry, but if you look at just three-level graviton exchange, there is singularity and
Yes.
0t.
yes, and as we've
There is
been
a pole
discussing,
which cannot be interpreted as any on-shell particle, is related to the presence of conical deficit and the fact that so isn't that singularity cannot be understood in terms of usual on-shell diagrams. So isn't that already suggests that analytic structure?
yeah. So we're basically assuming that issue is not affecting what we're discussing here. So of course, there's So that depends on. So we're yeah. So we're assuming that because it's a global effect and it's really not appearing with. It's not.
But this is part of the amplitude which you are constraining.
But are you saying that this is truly asymptotic state?
Right, but also
Yeah.
you
I mean,
just, but you calculate m, the amplitude, and it has this singularity. What do you mean? It's global effect because it's maybe I'm misunderstanding the object you're talking about.
I mean, the amplitude is just. I mean, of course, first of all, it's photon amplitudes. We're not talking about. So this is just matter.
Gravity because you I thought you have dynamical gravity, right? That means the full amplitude.
I mean, from the amplitude point of view, it's exactly the same thing as Chern-Simons theory, where the Chern-Simons matter theory, you don't have in Chern-Simons matter theory, you also there's another story, but you also have exactly the same T-channel pole, which even though the pole is there, but there's actually no physical degrees of freedom because it's just a Chern-Simons field. And since exactly the same behavior is all the discussion that you have, all the problem that you raise for this gravity problem is actually also there for the Chern-Simons. And from the Chern-Simons point of view, there's no conical defect. I mean, there's not non-gravitational theory. So I know that there's a connection between this and the argument, that connection of this with the conical defect, but I'm not sure that is actually affecting, because I have exactly the same problem in Chern-Simons theory. And then it's not related to any defect problem.
That theory has very peculiar analytic structure in the forward limit.
Yes. Yes.
In the case of gravity, it seems in the forward limit there's no issue instead. It's actually bad, huh? we kept this, just for the record, we kept discussing this issue all day.
To be recorded on the.
Yeah, exactly. So I think, unless there is a really urgent question, we ask you, we thank you.
Okay, thank you.
So before the coffee break, with a second, Filippo.